Are you ready? Are you ready? Now for the most amazing equation in mathematics. We are going to use our power series knowledge that we just talked about to derive the most incredible equation I've ever seen. And hopefully you'll find it as incredible as I do. So we're going to start out by writing out our power series approximation for e to the x to 11 terms. Okay, so here's our n equals 0, n equals 1, n equals 2, and so forth, all the way out here. Now, the second line here, I've substituted negative x for x. So notice every place we have an odd degree term, and I put a negative number in, it makes the entire term negative, because negative x cubed, for example, is negative, whereas negative x squared is still positive. So notice then that every other term in that bottom line is negative, whereas all the top numbers are positive. Now if I add the top line and the bottom line, on the left-hand side of the equal sign I have e to the x plus e to the negative x, and on the right-hand side everything that is odd cancels out when I add. So now I just have, and then I double everything, so now I have 2 plus 2 times x squared over 2 factorial plus 2 times x to the 4th over 4 factorial plus 2 times x to the 6th over 6 factorial plus 2 times x to the 8th over 8 factorial, etc. And it, the pattern continues. Now if I divide each side by 2, then I have e to the x plus e to the negative x all over 2 plus, or equals, equals 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial, etc. Now I want you to think which power series does this look like? Well, hopefully you said it looks like cosine, except for the fact that the signs need to alternate. Because with the cosine function it should be 1 minus x squared over 2 factorial plus, and so forth, plus x to the 4th over 4 factorial. So we are going to make it look like the cosine function by doing a clever little trick. If you look at the next line here, to make the signs alternate, so notice here this 1/2, see the e to the x plus e to the negative x, kind of like this, I just brought the 1/2 out front. But I substituted for x and negative x, I substituted ix and negative ix. So I'm taking this power series that I just came up with, this new one, and every place there's an x, I'm replacing it with ix. So I have ix squared, ix to the 4th, ix to the 6th, etc. Now recall that I squared equals negative 1 and I to the 4th is 1. So what's I to the 6th? Well, I to the 6th would be I to the 4th times I squared. So that would be negative 1. X to the 8th would be I to the 4th times I to the 4th, so it would be positive 1, and so forth. So when I actually raise these i's to powers, I'm going to get alternating signs. So this turns out to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, etc. So it turns out that 1/2 times e to the ix plus e to the negative ix is actually equal to cosine of x, because they have the same power series representation. If I went back and did something similar for sine, and I'm going to leave that to you. If you want to derive that and turn it into me, I'll give you extra credit. If you want to do a similar process and derive, it turns out 1 over 2i times e to the ix minus e to the negative ix is equal to sine of x. So notice this has an I in the denominator now, and then this is a minus. We are going to combine these two equations together, and by letting x equal pi. So instead of saying cosine of x, sine of x, I'm going to take cosine of pi, which means that the x's in the left-hand side of the equation will also be pi. So let's change that. So we have 1/2 e to the ix plus e to the negative ix. I'm sorry, I said I'm going to put pi in there and then I forgot to do it. What am I thinking? 1/2 e to the I pi plus e to the negative I pi equals cosine of pi. And 1 over 2I e to the I pi plus e to the negative I pi is equal to sine of pi. So now we just have to recall what sine of pi and cosine of pi equal. So let's think about here our little cosine and sine graphs. Sine graph, cosine graph, and we're looking at 1 pi, which is 180, which is right in the middle. So sine of pi is equal to 0, and cosine of pi is equal to -1 because it's down here. Now that I have that, I'm going to multiply both sides of my equation by the denominator of the fraction over here so that I can clear fractions. So let's see what this gives me now. On the left-hand side, I'll just have e to the I pi plus e to the negative I pi is equal to -1 times 2, which is -2. Over here, I have e to the I pi minus e to the negative I pi. And if I multiply both sides by 2i, of course the 2i's cancel over here, but on the right-hand side it's still 0 because 2i times 0 is still 0. Actually, that cancels. So now I have these two. Well, let's add those. E to the I pi plus e to the I pi is 2e to the I pi. And then the others, when I add them together, cancel out, and this equals -2, or e to the I pi is equal to -1. And another way of writing that is to say e to the I pi plus 1 equals 0. Either one of those is absolutely incredible. The second one's kind of interesting because it combines the 5 most fundamental numbers in math. 0 and 1 you recognize as being very fundamental numbers from the time you were in elementary school. Pi is completely fundamental to geometry. I is the imaginary unit. Without the imaginary unit I, we would lose the whole set of imaginary or complex numbers. And e turns out to be an extremely important number in math. The higher you go in math, the more e begins to even outshine pi. But all of these numbers appear over and over again in nature and in mathematics. And to combine them together and say that e to the I pi actually equals -1, let's think about that. E and pi are both non-repeating, non-terminating decimal numbers. I is an imaginary number. If you take e and raise it to the I pi power, you get -1. If you want me to demonstrate on my calculator, let's go to a new calculator page, add a calculator. Let's do this. So we go to our little button e to the, raise it to the power, to the negative I, so I need to get my imaginary unit here, I times pi, and let's push enter, -1. Pretty creepy, I think. Pretty amazing. I don't know what you want to call it, but this is an astounding thing that is true. That is called Euler's equation. E-U-L-E-R is how his name is spelled, Leonhard Euler. And that's what our math award is named about, if you heard that from our the math award night. But he's the one that first discovered this equation, and it's pretty amazing. So be amazed with me, enjoy, celebrate math.